Hello and welcome to this manufacturing process technology part 2 module 21. Today I would like to talk a little more about the kinematics and dynamics of ECM process as we were doing in the last module. And in the last module we had seen that how we could scale down the equations, the characteristic equations which would determine how the electrode, the inter-electrode gap would vary as a function of time. And we also further talked about how the scaled ratios may actually result in a situation where the y dash value goes to 1, that means the y actually approaches the equilibrium gap ye at a large instance of time, which is more or less t dash tending to almost infinity. So, today we are going to look at a slightly different aspect. One of them obviously, what happens if the feed motion is not sort of perpendicular to the electrode, but at an inclination with respect to the electrode surface. And when the feed velocity vector is inclined to the surface, the common approach that is taken is that a component of the feed normal to the surface is considered to be actually the feed which would result in the dissolution, etc. So, in this case the equilibrium gap now would be given by, instead of lambda by f equal to ye, it changes to lambda by f cos of theta. Okay. So, this is the component of the feed if the electrode is moving at an angle theta. So, it is a component of the feed perpendicular to the electrode surface that we are assuming in this particular case to be the actual feed. The other issue that I wanted to discuss is basically what happens when you are machining uneven surfaces. So, when an uneven work surface is subjected to ECM, as you know that ECM is sort of a leveler. So, it actually self levels the surface that we are machining, and metal is removed from all the portions of the surface. So, let us say if we have some portions projecting outward of a surface, for example, this is a portion which is projecting outward of this plane surface given by this dotted line, in this particular figure. So, this surface which can be recorded as a hill projected outside is obviously much nearer to the tool in comparison to a surface which is away, which is also recorded as a valley. Okay. So, obviously because the distance is lesser, the field in this particular case is more. So, the E which is equal to V by D in this case, as the distance is less, D is low, okay, is going to be higher in case of a hill in comparison to that of a valley. So, E hill is greater than E valley. So, obviously you all are also aware how the current density vector J is actually determined by looking at what is the electric field which is there in the electrolyte. And so, if the electric field is higher, the current density vector also is going to be higher, meaning thereby that the material removal rate q dot, which is again a function of the current density vector, will also be higher. So, the hills get removed more easily than the valleys. Okay. And so, therefore, ECM generally is a sort of a smoothening process. Okay. So, all uneven surfaces are self smoothened or self leveled because of this factor of variation of the electric field with respect to the tool side or the tool electrode. So, let us now look at some of the issues related to these uneven surfaces. We assume here certain things, that let us say if we make this gap right here to be the equilibrium gap at the equilibrium position ye, where you can say it is a condition where the dissolution rate is similar to the rate at which the feed is happening. Okay. So, corresponding to ye equal to lambda by f condition that we have discussed in the last steps. So, we want to see how the unevenness can be mapped in such a situation. So, in this particular case, for example, the unevenness plus delta in so far as a valley is concerned would be actually given by the actual y which happens to be the distance of the valley from the tool surface minus the equilibrium gap ye. Okay. That is how you can record the difference delta, you can call it plus delta or just normal delta as y minus ye, signifying that this is over and above the equilibrium gap because of the unevenness which is present on the workpiece surface. Similarly, you could have a hill recorded by minus delta, which would be again y minus ye in this particular case, where the y actually is lesser in comparison to the ye. So, that is how you see or characterize all the peaks and all the valleys which are there in the workpiece with respect to the tool once the workpiece has come to a equilibrium gap with respect to the tool. We are assuming the tool surface to be smooth, although that is really not the case. You can actually add the tool surface roughness also in this manner in order to project what these delta values would be. So, the deviations from the desired surface are the defects characterized by non-dimensional depths or heights delta dash. Let us look at how we will figure out the delta dash. So, obviously, we have one instance here, delta is y minus ye, as I had pointed out earlier, and so if I divided this by y in general, ye in general, that means I want to just map what is this delta in terms of the equilibrium gap ye, and call this the gap, the unevenness ratio, just as we had the gap ratio earlier. So, we can have delta dash equal to y dash minus 1 as our characteristic expression. So, we already have the equation for time from earlier, borrowed from earlier, equation for time ratio or the time variable t dash to be represented as y 0 dash minus y dash plus ln y 0 dash minus 1 divided by y dash minus 1. So, let us look at if we can figure out something related to the unevenness ratio or the unevenness non-dimensional number delta dash, just by assuming delta dash to be y dash minus 1 in a manner derived earlier here in this last step. So, therefore, the we can say that this y 0, this equation can further be written down as y 0 dash minus 1 plus minus of y dash minus 1 plus the natural log of y 0 dash minus 1 by y dash minus 1. So, this can be assumed to be a condition where y equal to y 0. So, therefore, we can call delta, or we can assume delta 0 dash to be equal to delta 0 by ye, which is actually equal to the y 0 at time point t equal to 0 minus ye divided by ye. So, this could be y 0 by ye minus 1, other words we can call it y dash minus 1, y 0 dash minus 1. So, y 0 dash minus 1 obviously is delta 0 dash, and similarly y dash minus 1 is delta dash. So, I have now an equation completely in terms of gap ratios given the the unevenness ratios given the gap ratios y 0 dash and y dash as t equal to delta 0 dash minus delta dash plus the natural log of delta 0 dash by delta dash. So, this is how the unevenness ratio varies. So, this is the unevenness at time point equal to 0, and this is the final unevenness or final roughness, you can say, of the surface. So, the final roughness is obviously a function of t, this is t dash, I am sorry, and also is a function of the initial roughness delta 0 dash, as has been illustrated in this particular equation. Okay. So, theoretically it would really take an infinite time to remove the defect completely, or in other words you approach a situation where this delta dash is 0, theoretically the t dash should be equal to infinity for that kind of a situation. So, that does not happen. Okay. But practically speaking, in how as soon as delta goes below a pre-assigned allowable value, the process is finished, and that is about the final roughness that can be obtained from an ECM process, and it is something which is of importance again for the industry as well, that what is the level of roughness up to which you can finish a surface. So, ECM is, although a self leveling self evening process of a otherwise uneven surface, it cannot go beyond the capacity of the process to do the self leveling, and so that is the limited, this is the limit delta dash that would finally arrive at, which is also known as the process tolerance in an ECM. Okay. So, that is how you take care of this term here called process tolerance in ECM. Let us now try to look at again the T dash delta dash characteristics, just as we did the Y dash T dash characteristics. So, here in this particular illustration, for example, on the Y axis it is clearly shown depth of ECM in equilibrium gap units required to achieve the indicated tolerance level, and the tolerance level that is indicated is mentioned here as 0.01, 0.02, 0.05 and 0.10. So, typically if this is the finished tolerance corresponding to, let us say, time T dash equal to infinity, or this is the capability of the process as I was talking about earlier, the way that this depth of ECM in equilibrium gap units would vary with respect to the initial defect size delta 0 dash lies on this particular curve. Okay. So, if we start with some initial defect size, okay, we can actually predict what is going to be the depth of ECM that is needed to start with, okay, where you could actually hit upon a certain final tolerance delta dash. So, that way you could actually look at this graph as sort of a thumb rule or a parametric curve to estimate the start point, or the value of y really from which you need to start for the tolerance system to approach a certain level. And here as you can see that when we talk about the positive delta 0 dash, meaning thereby these are all corresponding to the valleys. Okay. So, the valleys are a little more harder to machine than the hills, which are corresponding to the minus delta 0 dash side, and so the valleys get removed less easily in comparison to the hills. Okay. So, that is how we can sort of predict the tolerances, the final tolerances of an ECM process. So, let us now work out some numerical examples to find out whether we can really estimate the equilibrium gap, considering certain aspects are related to the ECM process, like for example, if we have the design over voltage, the design voltage, and some of the other material removal rates, etc., that can be predicted in this manner from conductivity of the solution, atomic weight, etc., can we really predict the equilibrium gap? Okay. So, let us say in an ECM operation with flat surfaces, a 10 volt DC supply is used and there is an over voltage of 1.5 volts that you need to assume. I would like to also maybe delve into an area where we eventually predicted, as I had earlier illustrated through our Debye-Heckel process, what would be the zeta potential of a surface, okay, against which the electrolyte flow must happen for electrochemistry to occur. Okay. So, this is also a part of such the overall over voltage potential. So, I am just giving a value here for ease of working out. The conductivity of the electrolyte is given to be 0.2 ohm inverse centimeter inverse, and a feed rate of 1 mm per minute is used, and the workpiece is made of pure iron. So, the characteristic properties that we assume here is corresponding to an atomic weight of iron, which is 55.85 grams. We assume the lowest dissolvable valency state of +2, iron comes into ferrous ions. The density of iron, which is 7.86 grams per centimeter cube, and if we look at now the equilibrium gap YE, which is otherwise given by lambda by F, in other words could be given by K times of A times of V minus delta V divided by rho Z into Faraday constant capital F times of the feed rate in millimeters in centimeters per second. So, because we want to convert everything into centimeters units and second units, because current again is represented in that manner. So, we now have here substituting the value of K 0.2 times the atomic weight, which is 55.85 times of total available voltage, which is voltage minus over potential 10 minus 1.5 divided by the density of the material times the valency times 96,500 coulombs times the feed rate here, which can be recorded as 0.1 centimeter by 60 seconds. So, this is in terms of centimeter per second, 0.1 by 60. So, we just record this value here 0.1 by 60, and so if we calculate the YE value comes out to be equal to 0.04 centimeters or 0.4 millimeters, okay, corresponding to about 400 micron. So, that is how small the equilibrium gap comes out to be in such a case. So, theoretically the equilibrium gap can have any value, but in practice the tool and the work surfaces are never perfectly flat, and so it really depends on what is the average roughness, which would be deterministic of this term YE. So, if supposing the equilibrium gap is too small, then the surfaces may match each other, and this may cause a short circuit because of irregularities of the electrode surface. So, this is something that we have to avoid in a ECM process, the touching or the short circuiting of electrodes owing to the differential surface roughness. So, let us look at another problem example which talks about the minimum possible equilibrium gap that needs to be maintained given a certain surface roughness value that has been provided. So, let us say in this particular case the surface irregularities of the electrodes with the flat surfaces are 5 micron and 8 micron. You can see the irregularities plotted here. This is obviously a very evenly realized surface. Real life situation is not so even. So, the surfaces are going to be completely random in that case. So, in that event the surfaces that you would, or the parameters that you would take to determine is really the Z maximum, for both the surfaces. So, these are the heights of the peaks of asperities. If the work is of pure iron and a DC voltage of 12 volt has been employed, you have to estimate the largest possible feed rate that can be used in this particular condition. In other words, feed rate and equilibrium gap are almost related to each other. So, you are estimating what is going to be the minimum equilibrium gap at which you can operate. So, assume the conductivity and over voltage to be same as the previous example, and also assume that the surfaces are made up of iron. So, having said that, the minimum allowable value of the nominal gap so that the electrodes do not touch each other is given as 8 microns plus 5 microns, that is about 13 micrometers, and therefore, the YE or the equilibrium gap can be recorded as 0.0013 centimeters. Okay. So, once this YE is recorded, it is very easy to calculate the maximum feed rate, which would depend on Ka V minus delta V divided by rho Z F times of this YE, and this YE maximum or YE minimum that can be allowed has been given out to be 13 microns. So, if I substitute the values of K 0.2, 55.85 times of the same, potential over potential divided by 7.8 times of 76,500 times let us say plus 2 valency state times this 0.0013 centimeters, what I get is 3.57 centimeter per minute. In other words, I can go at a maximum feed rate of 35.7 millimeters per minute. Okay. So, that is how you can consider the maximum feed rate to be in this particular example problem. So, I think now you should be enabled to sort of do some numerically designed problems about how to predict the equilibrium gap, the minimum equilibrium gap, the maximum feed rate, so on and so forth, if you get across an ECM setup and try to start doing ECM machining. The other issue that is important for me to tell or share at this level is that it is very important to ensure that the heat transfer processes which are working in a ECM setup are well managed or well balanced. And one of the reasons why that is so is that the electrolyte starts behaving ohmically, and it is a conductor, and so obviously there is going to be heating of the electrolytes. So, we can think of that the electrolyte serves as a sort of a heat sink which goes into the working zone, gets all the heat, and because it is a flowing electrolyte, it is actually a working fluid for the heat transfer from the electrode to happen. So, if we assume a simple one dimensional model, we should be able to ensure that the temperature of the electrolyte never goes above its melting point, so that there are no problems related to bubbles, etc. Bubbles can be of serious consequence in ECM. I am going to probably do this in great details once we talk about surface finishing and what are the kind of issues which are involved in the ECM process. But as of now, I would like to just illustrate that there is something called a velocity design in the ECM process, and the next step that we are going to follow is to sort of try and see if we can get the velocity of the electrolyte flow in an ECM setup, which gives you a workable system where there are no evaporation issues, there are no bubble formations of the electrolyte in such a setup. So, let us look at this temperature and pressure during the ECM, and we will just simply use a one dimensional problem here. So far as the machining forces are concerned, it may appear at first glance that forces acting on the tool and the workpiece are negligible, since material removal takes place at atomic level. But since the electrolyte has to be provided with an adequate rate of flow, normally the pressure is large. So, this is something that we must understand. Number one, the gap of an ECM setup is very small because of the smallness of the minimum equilibrium gap that is possible depending on the surface roughness level of both the electrodes. So, when you pass a fluid at a certain velocity through such a small gap, so there is obviously going to be a lot of shear between the surfaces concerned, particularly the electrode surfaces and the rushing electrolyte, and the shear is always resulting in a pressure which would be in the typically the reverse direction of the flow, and so that is one aspect. And obviously, when you are moving a narrow gap, when the surface is more prominent, the factors which are related to the bulk or volume flow of the fluids become insignificant compared to the surface related factors. So, the hydrostatic forces would although act on the tool and workpiece, they are caused because of the shear as well as the hydrostatic pressure, and sometimes it may lead to the warping of the electrodes. And the condition that needs to be arrived at really is that such a pressure because of shear or any other factor, okay, would not increase or exceed the ultimate yield strength of the material. So, therefore, it is very important to design the electrolyte flow in such a manner so that you do not avoid the ion concentration to take place, so that it is not that as if in one area or one section there is more machining in compared to other because of the exceedingly high ionic concentration which accumulates in different areas. You should avoid the deposition on the tool, that is another reason why flow should happen of the electrolyte. It should be able to remove the precipitation, whatever you know that the ECM process is all about ferrous converting into ferrous hydroxide and getting precipitated. So, somebody has to be able to swipe the area of the precipitate which is getting formulated. So, flow is very important for that aspect, and then obviously to avoid overheating of the electrolytes and to also ensure that the pressures are within reasonable level, you need to ensure that the electrolyte flows at a pre-designed value. Last one, this overheating, and of course, the pressure rise therein is a very serious consequence. It is very important, and an estimate of the required flow rate of electrolyte has to be worked out just because of such a perennial problem which may exist in all ECM setups. So, I would like to sort of start with this model from the next module, but I will just like to mention the basic premise that we would have to take into account for modeling. So, you have now a tool surface, as you can see here in a workpiece surface, and we assume that the electrolyte has to flow in at a certain temperature theta 0 from this end of the ECM, and it goes out from this other end of the ECM, where the electrolyte temperature gets elevated because of the heat transfer which would happen from the tool into the electrolyte from theta 0 to theta 0 plus delta theta. So, having said that, we would like to just analyze a small element of fluid of thickness dx, which is otherwise spaced for a certain distance into the plane here. Although it is a 2-dimensional problem, we would need not assume this to happen. We can consider the distance into the plane in the z direction to be unity. But even if you do that by considering some distance, let there be some distance in the z direction as well. So, you are essentially talking about a cuboidal element of the electrolyte, and you would like to consider the current flow across the cuboidal element and try to also see what is the temperature enhancement because of such a current flow. So, we will do this model at probably one of the later modules, and I am going to close on this module in the interest of time. So, thank you very much for being with me.